So just to recap us again, alright, contact surface, we are still talking about surface contact, how to calculate it. Alright, there's a more important term, the Hertzian stresses. Alright, so we talked about Hertzian stresses in the single contact in the previous video. So regarding this page, alright, page 17. Now we're going to talk about Hertzian stresses in the two curved surface. Alright, page 18. Alright, where two curved surface speaks about when you start to rotate certain curved surface. Alright, so single contact, if you in fact if you never see that previous video before, please take a look at the previous video. Nonetheless, I'll explain it now also. So you press this down, you indent the material, right? Indent the material. If this material is very hard, alright, you indent this piece of surface. Okay, so if you indent, this is called a single contact because there's only one thing that is contacting on the surface of the material. Okay, if it's a two curved surface, imagine this is the shaft, alright, it's rotating, alright, and you have certain bearing, this bearings over here, alright, and you have a rigid shell casing. Nonetheless, I will have a lot of bearings lah, this bearings all over here. Okay, but let's take a look at this. So if you turn this thing over here, this ball bearing will actually turn over here. But because of contacting surface over here also, and this is what it's trying to resist another friction over here. So as you can see, there is two contact surface, and this is why it's called a double curved surface, because it's curved, and that's why it's called double curved surface, double curved contact surface or whatever. Hopefully you get the meaning. So let's take a look on the equations of the double curved surface. So since there's a two curved surface, the visualization of the maximum stress is very tough. Alright, but you need to know this equation. No need to memorize, I think. You give me a while, I take a look. So you no need to memorize this one. Alright, so they'll give you this thing. This thing is the weight of the forces acting on the material. Alright, so I think they'll give it to you, or I think in the future I'll update to you what is how to calculate the W. So W is called the normal contact force. Alright, so in terms of the Newton forces. And therefore when they say the compression force, then you can use this thing also. So if it's got compression force, then you use this. Yeah, most probably, yeah, because it's compression force. But anyway, so this is the Young modulus, the equivalent Young modulus, I think. It's the equation that I've shown you in the previous video. This equation. So you need to memorize this one. You need to know your Young modulus, your Poisson ratio. Okay. So once you know this, alright, E1 and E2. Normally, for metal, E1 and E2 should be the same, I believe, because from some equation that I see some answer tutorial, this is what it's saying. Instead of because normally steel is isotropic material, meaning taking in stress in all directions, taking the same stress. If it's an anisotropic material, then it's only taking in one side of stress. Alright, it's strong in only one side, the rest is weak. Alright, then you're gonna know about these things, but at least you know the stuff. So let's come back here. So you need to find your equivalent Young modulus, as I mentioned just now. You need to also find this equation. You need to memorize this one. It's the mean contact radius. Alright, so it's 1 over R1 divided by 1 over R2. So I believe it's like a average contact radius between this radius, this turning shaft, and the ball bearing radius. So it's in between them. You want to talk about the radius in between them. I don't know how it works, but you just need to know that. Alright, take note it's a absolute value, so if you have negative values, never mind. No need to panic or whatever. Okay, and then you also need to find your A, which is your impression radius. Alright, where it's impressing onto the surface. Alright, it may be pressing onto this surface also, this surface. So this impression radius is calculated by this thing. Alright, the same thing, your calculations, everything, your R, your E are all over here. So you just sub in values, that's it. Okay, if you don't know what is impression radius, you can go to the previous video and watch. Alright, I know I don't want to explain. Same thing, the shear max or the shear strain, the amount of shear shear stress, maximum shear stress is 0.5 to 0.7 A is the peak shear stress is 0.5 to 0.7 A. That's all it is. Okay, the location of it. Okay, the location of it. Then the shear max is equals to stress. Give me a while. Now let's take a look. So this is the shear stress now. So in other words, right? Give me a while. Really. So what we have done just now is to calculate our shear max or maximum shear stress. That is, sorry, the maximum stress. What am I talking? This is the maximum stress. Maximum stress of the ball bearing. How well can it sustain certain stresses? So we are talking about that. All right. So if you're talking about that, all right. Now we also need to talk about the maximum shear stress. Just now is maximum stress. This is now maximum shear stress. Different. Okay. So in order to determine the maximum shear stress, you need to take the yield stress of your material. Alright, single unit axial stress state. So previously in previous video, right, we have this surface and then we impress it. We have a certain radius, and then we say that the shearing, the location of the shear stress is this is the shear max of the single contact. Now we're talking about single contact, which is related to previous video. Okay, is equals to 1/3 of the maximum stress, right? So in this case, right, because now we are talking about two contact surface, right? Because the ball bearing is contacting on here and also here. So by right, we may think that it is 2/3 now, but end up, right, it's actually also about 1/3, and the location is somewhat 0.6. Alright, and this is actually coming from this reading material, which helps you to understand better. Okay, so I suggest you read it out. So the word like principal radii of curvature, alright. Oh, okay, it's the plural form for radius. Never mind, I thought it was like some chim words. So yeah, it's the principal radius. So you need to know the radius, and then yeah. So the results from the above solutions are somewhat surprising, since they show the maximum shear stress occurs below the surface and blah 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 blah. You can read yourself. Okay, please read. Alright, I pause the video and read. Alright, so over here, right, this is the maximum stress. Why am I keep saying maximum stress, alright, at P max. Okay, and let me see. If you were to draw this thing, alright, this is the ball bearing. Okay, and this is the surface that is contacting it, and this is the shaft part. Okay, so when you hit it, right, this thing over here will actually impress it. This thing will kind of impress it, right? So this impress has a certain impression radius, as we've said just now in the previous video. Alright, so this impression radius is being shown over here. Alright, where the impression radius is A. Okay, same thing over here. There will be also another impression radius, because it may actually hit onto the surface, so there will be another impression radius A. Alright, so the location of the maximum shear stress is 0.6 of the A. Okay, it's the same thing, just previous video, maybe I should say 0.5 to 0.7. I mean 0.5 to 0.5 to 0.7. So it's 0.6 plus minus 0.1 uncertainty. Okay, this is how it works. Alright, and therefore if you come back here, alright, so why this? Because you see, as you said, you can see the amount of stresses that is consolidating over here. This is the lines for linear stress. So over here there's a lot of lines, and as you disperse and disperse, there's lesser and lesser linear stresses. Alright, I mean lesser and lesser stresses, shear stress. These lines are shear stress, sorry. Yeah, so over here this is more of a lot of shear stress going on, and this is why a lot of shear stress that comes around here is about approximately 0.6 A. Alright, hopefully you are kind of somewhat clear. And in fact the maximum stress, I think, is at this point, at this part. Alright, I don't know, but something for you to think about it. Alright, so after that, right, there is one interesting information also, is that as the pressure of the surface increase beyond 3.1 K, K is the constant, alright, a plastic zone will form, but the material will be unable to flow. Alright, so once it reaches the three times thing, alright, so for example, if your or stress max is, if I never understand wrongly, or if I never understand wrongly, so I may be wrong also, is that your material over here, okay, so if you have a flowing, so you may actually, the pressure at the surface may increase beyond 3.1, alright, or the 3 times of your stuff or whatever lah. Okay, it may actually will deform a bit, however it will not deform due to the fact that the shear that is unable to flow, alright, because it's unable to flow, so it's somewhat being controlled by the shearing part. Alright, although there is a certain maximum stress, but it will not deform because the shear stress, because there is a so-called criteria. So in order to deform, you will need your shear stress, alright, to reach the yield stress, alright, which will happen when the contact stress is approximately 6K instead of 3K. I know my explanation sucks now. Yeah, give me a while. Alright, so over here it says the K is actually yield stress divided by 2. Okay, so it's yield stress divided by 2. So if it's 3K, then it's talking about 2/3. Give me a while. Yeah, so the shearing part is 2/3 of the yield stress of the material. Alright, with this equation. Okay, because as it says the 3K the contact surface. Where am I? Yeah, give me a while, I come here. Alright, so there will be a beyond 3K stuff. So if it's K is equals to yield stress divided by 2. So as the pressure of the surface increase beyond this 3K, plastic zone will form. Why am I talking weirdly? But the material will be unable to flow until the shear stress at the surface reaches the yield stress. Because why is unable to flow? Because once it reaches here, it will start to deform. But however, at this point, it will hard to deform, right? So therefore, you need to talk about the amount of stresses trying to deform, trying to twist this thing, trying to twist your ball bearing apart. So your ball bearing will end up something like that. Right, a bit twisted. I don't know how to draw but at least you get what I mean. Alright, so you will need, in order to do this, you will need about 6K. So 6K, K is equals to this one. So 6K will be 6K is equals, yeah, so it will be yield stress divided by 12. Alright, so this means that it will require higher stress, higher yield stress, lower yield stress, is it? Never mind, I'll let you think about it But then you know that your H is equals to 6K is equals to 3 times the yield stress of the material, and K is equals to the shear stress of the yield stress of the shear, the yield stress of the shearing. So over here K is equals to divided by 2, and over here, over here is divided by 2, over here is directly equals to each other. So you know, a bit weird now. That's why it's a bit confusing here and there. But nonetheless, you need to take note of this value. So the H is the indentation hardness. Alright. So what implies is that the higher the value it is, alright, the better it is lah. Alright, so it's harder. Alright, so therefore if it's harder, then you will withstand more high contact pressures. Alright, because 6K is equals to 3 times of the yield stress. I mean shear yielding. Alright, things like that. So if K is equals to sigma y over 2, yeah, I don't know how the math works lah. Alright, a bit lazy already, but you just need to take note of that. Oh, okay. So 6K is equals to 3 yield stress. So if I were to bring K is equals down, so I will have 3 times this one divided by 6. So I'll have yield stress divided by 2. So my K is equals to this thing. So this is why the lecturer has written it down over here as this one. So you just need to memorize this one, okay? So yeah, that will be better. So cancel off whatever I say. Alright, so for plane stress, alright, plane stress, take note of plane stress, the word. Alright, your shear, maximum shear is yield stress divided by 2. Alright, so there will be a confusing part all along over here. That's the thing. So then never mind. So yeah, you just need to know that the maximum shear stress is this one. Important. Okay. And then next we will talk about the Brenner's hardness test method in the next video. So hopefully you kind of understand briefly about here and there for the double curved surface type of thing. Alright, so yeah, so take note of this picture also lah. Alright, because over here there will be a contact surface, so this thing over here there will be a stresses, there will be also a stresses. So as you think about it, the mean contact radius, alright, will be in between them. Alright, so it's trying to give the overall average. Alright, the contact radius, I don't know how to draw lah, but at least you get a meaning of that also. So I think that is it for this part lah, for the two curved surface part. So previous video was single contact, so now it's a two curved surface. So I think this is okay. So next, right, we will talk about the testing, alright, which is how to calculate acceptable surface thickness. So I think we know how to calculate the surface thickness already. So we also need to know the testing part. Alright, so in the next video we'll talk about testing. So surface thickness you need to know is the shearing part. Alright, it's 0.6 plus minus 0.1 A. Okay, the A is the impression radius. Alright, and I think this is it lah. So next video we'll talk about the Brenner's testing. See you there.